Welcome to Jeremy's IT Lab. This is a free complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. In this video, we'll look at LAN architectures. By architectures, I mean how devices like routers, switches, PCs, servers, etc. are connected together to make networks. These LAN architectures are exam topics 1.2a, b, c, and e. 2-tier, 3-tier, spine leaf, and small office home office. The other topics in 1.2, 1.2d, which is WAN, and 1.2f, which is on-premises and cloud, will be covered in separate videos. Here's what we'll cover in this video. Actually, it's exactly the exam topics I just pointed out. First, we'll cover 2-tier and 3-tier LAN architectures. These are common traditional LAN designs used in enterprise networks. Then we'll cover spine leaf architecture, which is a design common in data center environments. Finally, I'll briefly cover SOHO, small office home office networks. Small networks like this are different than the others in that they typically have a single network device acting as router, switch, firewall, and wireless access point. Watch until the end of the video for a bonus practice question from Boson Software's ExSim for CCNA, my recommended practice exams for the CCNA. Before actually getting into the topics for this video, let me introduce why this section of the course is important. You have studied various network technologies up to this point in the course, such as routing and switching, STP, Ether channel, OSPF, FHRPs, switch security features, etc. So, now let's look at some basic concepts of network design and architecture. Network design is a very deep topic, and to be a good network designer, a good network architect, requires a deep understanding of general principles, as well as the needs of the specific customer. Although there are standard best practices for network design, there are very few universal correct answers. The answer to most general questions about network design is, it depends, because the requirements of each network are different. Now, in the early stages of your networking career, you probably won't be asked to design networks yourself. That's usually left for the more experienced engineers. However, to understand the networks you will be configuring and troubleshooting, it's important to know some basics of network design and architecture. So, in this video, and the next few, we'll cover some basic concepts. And now, before introducing the 2-tier and 3-tier LAN designs, which are the main topics of this video, I want to briefly introduce a few common terminologies you might hear, and which I might use throughout this video. These are general terms, not only for LAN design, but for connections between devices in general. The first one is called a star topology. When several devices all connect to one central device, we can draw them in a star shape like below. So this is often called a star topology. In the diagram below, all PCs connect to one central switch, and I have placed them in a star shape around the switch. Note that in network diagrams, the devices might not be drawn like this, in the shape of a star. But if many devices are all connected to one central device, we can call it a star topology, regardless of how the diagram is drawn. The next term is full mesh, which is when each device is connected to each other device, forming a mesh. Here's an example. 6 routers, and each router is connected to each other router. This is called a full mesh topology. The last one I want to introduce is partial mesh, which is when some devices are connected to each other, but not all. Here's an example with 4 switches. Notice that the top 2 switches are both connected to each other switch, but the bottom 2 switches are not directly connected. This is a partial mesh topology. Okay, those are the 3 general terms I wanted to introduce. You'll see examples of them throughout this video and the next video, so make sure to remember them. Now let's get into the basics of Campus LAN Design. By Campus LAN, I mean a LAN of devices in a building, or perhaps multiple buildings that are close to each other. Remember, LAN stands for Local Area Network. First, we'll look at the 2-tier LAN design, which consists of 2 hierarchical layers, the access layer and the distribution layer. The 2-tier design is also called a collapsed core design because it omits a layer that is found in the 3-tier design, the core layer. Or more accurately, it combines the two together into one layer. So in the next slide, I'll show you an example of a 2-tier design, but first let me summarize each layer. First, the access layer. This is the layer that end hosts connect to, for example, PCs, printers, security cameras, etc. They will usually connect to an access layer switch. So typically, access layer switches have lots of ports for end hosts to connect to. QoS marking is typically done here. This is the layer that end hosts connect to, so we usually mark traffic here because it's a good practice to mark traffic as early as possible in the network. Security services like port security, DAI, etc. are typically performed here too. Also, switch ports might be PoE, Power over Ethernet enabled, if there are wireless access points or IP phones in the LAN. So that's the access layer, the switches that end hosts connect to. Then there is the distribution layer. These switches aggregate connections from the access layer switches. So depending on how many end hosts there are, your network might have many access layer switches. Those connections are then usually aggregated to a redundant pair of 2 distribution layer switches, as you'll see in the next slide. Typically, this is the border between layer 2 and layer 3 in the network. So the distribution layer switches run both layer 3 protocols such as OSPF and layer 2 protocols such as spanning tree. This is not always the case, but usually the connections from the access layer switches to the distribution layer switches are layer 2 connections, and then end hosts use the SVIs on the distribution layer switches as their default gateways. The distribution layer is used to connect to services such as internet, WAN, etc. Okay, let's look at an example. Here's a simple 2-tier campus LAN network. The 2 access layer switches, A1 and A2, each have some different end hosts connected, and each also has a wireless access point connected too. D1 and D2 are the distribution layer switches, and each is connected to both A1 and A2. This provides redundancy by having extra connections in case one fails. However, the connections between the access layer and distribution layer are layer 2, and that means loops can occur. So, spanning tree protocol disables a few links to prevent loops. Now, D1 and D2 are multi-layer switches, and the end hosts use the SVIs on D1 and D2 as their default gateways. So, they will probably be using a first-hop redundancy protocol such as HSRP or VRRP to provide a redundant virtual IP address for hosts to use as their default gateway. As I said before, the distribution layer is used to connect to services such as the internet or the WAN, as well as other parts of the LAN. So, here's the connection to the internet. 2 redundant connections to 2 different internet service providers. And perhaps there's another set of distribution and access switches over here, with lots of servers connected to the access layer switches. Notice that each distribution layer switch is connected to each other distribution layer switch. By the way, in a collapsed core 2-tier design like this, the distribution layer is sometimes called the core distribution layer, because it has to fulfill the purpose of both layers. We'll see the core layer later. These connections between distribution switches are layer 3, no spanning tree running here. Routing information can be shared via OSPF, for example. So this is an example of a 2-tier network architecture. The end hosts connect to the access layer, which performs things like QoS marking, security features like DAI, etc. The distribution layer switches aggregate those connections and then connect further to services like the internet and to other parts of the LAN. Now let me relate this back to those common terminologies I mentioned at the beginning. Although I haven't drawn the diagram like a star, at the access layer, we have many devices all connecting to one central device, each access switch. So these are 4 small star topologies. If I put more end hosts on the diagram and arrange them around each access switch, it would look more like a star, but I think you get the point. And here we have a couple partial mesh topologies between the access layers and the distribution layers. Notice that the distribution switches are connected to each other and to each access switch, but the access switches aren't directly connected. So these are two partial meshes. And finally, between the 4 distribution layer switches, we have a full mesh. Each distribution switch is connected to each other distribution switch, forming a full mesh. You'll see elements of full mesh, partial mesh, and star topologies in all kinds of network designs, and often combinations of them, sometimes called a hybrid topology. So once again, make sure you remember these terms. Now, if the network gets larger, we might have many distribution layers connecting to different parts of the LAN. Do you see anything wrong with this? In large LAN networks with many distribution layer switches, for example in separate buildings across a campus, the number of connections required between distribution layer switches grows rapidly. This makes it much more difficult and complicated to scale the network, to make it bigger. So, to help scale large LAN networks, you can add a core layer. By the way, Cisco recommends adding a core layer if there are more than 3 distribution layers in a single location. In this case, there are 6, so we should add a core layer. Here's how it looks with a core layer added. Each distribution layer connects to the core layer. No need for a full mesh of direct connections between the distribution layer switches. These core layer switches are a pair of very powerful and fast switches. So let's take a look at how the core layer works now. When we add a core layer, we now have a 3-tier LAN design: access, distribution, and core. Let's talk about that core layer. It connects separate distribution layers together in large LAN networks. The focus of this layer is speed. You might hear the term fast transport as being a goal of the core layer. CPU-intensive operations such as security features, QoS marking and classification, etc., should be avoided at this layer. We just want fast forwarding of packets, nothing extra. And the connections are all layer 3. We definitely don't want spanning tree at the core layer. The core layer should maintain connectivity throughout the LAN, even if devices fail. Because it's the backbone of the LAN, redundancy of devices and connections is very important. Let's take a look at the previous topology with an added core layer. Here's how the network might look with the addition of a core layer. This time, the core switches connect to the internet routers. And if we have additional distribution and access layers, where will they connect? As you know, they will also connect to the core switches. So this is an example of a 3-tier campus LAN. For smaller LANs, 2 tiers is sufficient, but larger LANs will likely have 3 tiers like this. Okay, let's review those tiers once more and then move on. Here are those attributes of each layer again. For the access layer, remember that it is the layer that end hosts connect to, and it often performs services like QoS marking, port security, DAI, DHCP snooping, etc. For the distribution layer, remember that it is all about aggregating connections from the access layer and serves as the border between the layer 2 network and the layer 3 network. In a 2-tier design, it connects to services such as the internet and WAN, although in a 3-tier network, usually those connections will be to the core layer instead. Notice I added an extra note, saying that it is sometimes called the aggregation layer. Remember that, as aggregation of connections is an essential function of this layer. Finally, the core layer is used in large LANs to connect distribution layers together, and the focus is on speed, so we avoid operations like security and QoS marking and classification. All connections here are layer 3. Okay, that's all for the 2- and 3-tier campus LAN designs. Keep in mind what I said earlier. There are very few universal correct answers in network design. Although these 2- and 3-tier LAN designs are common practice and recommended by Cisco, in the real world there are countless variations depending on the needs of the enterprise. Let's move on to the topic of spine leaf architecture. This photo I'm showing you was taken in a data center, and the reason why I'm showing you it is because spine leaf architecture was designed for data centers. Currently, I work for a large data center provider, so I spend a lot of time in environments like this. So what exactly is a data center? Data centers are dedicated spaces or buildings used to store computer systems such as servers and network devices. They typically contain halls of racks, like the previous photo, and the servers and network devices are mounted onto the racks. Traditional data center designs used a three-tier architecture: access, distribution, and core, like we just covered. This traditional design worked well when most of the traffic in the data center was north-south. What does that mean? Well, if we look at this diagram, north-south refers to traffic from the access layer up to distribution, core, and then perhaps out to the internet, or back down south to the other distribution and access layers. These other sections of the LAN are drawn off to the side, so the traffic doesn't look north-south when drawing the arrows in this diagram, but this is north-south traffic too, of course. This is in contrast to east-west traffic, which is, for example, traffic between these servers in the same part of the network, like this. The traffic doesn't go out to other parts of the LAN or out to the internet. With the precedence of virtual servers, which is a topic I'll cover soon in the course, by the way, applications are often deployed in a distributed manner, across multiple physical servers, which increases the amount of east-west traffic in the data center. If you're not sure what a virtual server is, or you don't know what virtualization is, like I said, I'll cover it soon in another video. Anyway, the point is that with this increase in east-west traffic, the traditional three-tier architecture led to bottlenecks in bandwidth, as well as variability in the server-to-server latency, depending on the path the traffic takes. To solve this, spine leaf architecture, also called CLO architecture after the name of one of the designers, has become prominent in data centers. Let's check it out. Here's what spine leaf architecture looks like. It's two-tier, but different than the traditional two-tier design we looked at before. There are spine switches and leaf switches, and here are the basic rules about spine leaf architecture. Every leaf switch is connected to every spine switch. If you look at the diagram below, there are 3 spine switches, and each leaf switch has 3 uplinks, 1 to each spine switch. Therefore, every spine switch is connected to every leaf switch too. However, leaf switches do not connect to other leaf switches, and spine switches do not connect to other spine switches. Finally, end hosts, for example servers, only connect to leaf switches. They are like the access layer of the spine leaf architecture. Okay, those are the main rules of spine leaf architecture. The path taken by traffic is randomly chosen to balance the traffic load among the spine switches. And each server is separated by the same number of hops, except those connected to the same leaf switch, which have fewer hops, of course. And this provides consistent latency for east-west traffic between the servers. For example, for this server on the left to reach this other server, the traffic passes through 3 switches. And then to reach this other server, it once again has to pass through 3 switches. So that's spine leaf architecture. It's also very simple to scale, because if you need to add more servers, you can just add another leaf switch and connect it to the existing spine switches. As with all topics in the CCNA, there is a lot more depth to spine leaf architecture than what I just mentioned, but make sure you know these basic characteristics of spine leaf for the CCNA exam, and you should be set. Now let's move on to the final topic. That final topic is SOHO networks. Small office home office, also called SOHO, refers to the office of a small company, or a small home office with few devices. Now, it doesn't actually have to be used as an office. If your home has a network connected to the internet, it is considered a SOHO network. SOHO networks don't have complex needs, so all networking functions are typically provided by a single device, which is often called a home router or wireless router. There is no need for a dedicated device for each function. This one device can serve as a router, connecting the home network to the internet. Also a switch, as there are usually a few switch ports on the back to connect other devices too. Also, there are usually simple firewall functions, typically configured to block all connections coming from the outside network, but to allow connections to the internet from internal devices. It also serves as a wireless access point, allowing you to connect your laptop or phone, for example, to the network using Wi-Fi. Also, in some cases, it can serve as a modem too for cable internet, although sometimes the modem is a separate device. Here's an example of a simple home router, although they come in all shapes and sizes. For very small networks, there's no need to have a separate device dedicated to routing, a device dedicated to switching, a device dedicated to providing wireless access, etc. This one device can do it all. So, although an enterprise network would have these all as separate devices, the home router combines them all into one small device. Now, throughout this course, we are focusing on enterprise networking. Very small companies, or home offices, don't have the need, or probably the resources, to hire a dedicated network engineer. So they often just rent a wireless router from the ISP, and that serves their purposes. Here's a review of what we covered in this video. First, traditional 2-tier and 3-tier LAN architecture. Make sure you know the 3 layers: access, distribution, and core, and their basic characteristics. Then I introduced spine leaf architecture, which is common in modern data center environments. Again, make sure you know the basic rules of spine leaf and its characteristics. Finally, we took a brief look at SOHO, small office home office networks. They are small networks that typically have a single networking device that provides them with routing, switching, security, and wireless access. As always, watch until the end of the quiz for a bonus practice question from Boson Software's ExSim for CCNA, my recommended practice exams for the CCNA. Okay, let's go to quiz question 1. Which layer typically serves as the boundary between layer 2 and layer 3 in a traditional 2-tier or 3-tier network? Pause the video now to select the best answer. The answer is B, distribution. Typically, the connections from access layer to distribution layer are layer 2, and they run spanning tree protocol. The connections from distribution to core are layer 3. So the distribution layer serves as the boundary between layer 2 and layer 3. Okay, let's go to question 2. Which of the following would you not expect to find in the core layer of a traditional 3-tier LAN? Pause the video now to select the best answer. Okay, the answer is B, STP, spanning tree protocol. Because the connections at the core layer are all layer 3, spanning tree protocol should not be running in the core layer. Okay, let's go to question 3. At which layer would you expect to find PoE-enabled switch ports in a traditional 3-tier LAN? Pause the video now to select the best answer. Okay, the answer is A, access. Devices that use PoE, like wireless access points, IP phones, and IP security cameras, all connect to the access layer. So that's where PoE-enabled ports can often be found. Okay, let's go to question 4. In a spine leaf architecture, which of the following should not be connected to a leaf switch? Pause the video now to select the best answer. The answer is B, a leaf switch. Endpoints like servers can connect to leaf switches, and each leaf switch should connect to all spine switches, but leaf switches should not connect to each other. Okay, let's go to question 5. Which of the following functions might be included in the device known as a wireless router? Pause the video now to select the best answer. Okay, the answer is F. A wireless router, also known as a home router, is a multi-purpose network device that can provide routing, switching, wireless access, security features, etc. for a small network. This kind of device is often used in SOHO, small office home office networks. Okay, that's all for the quiz. Now let's take a look at a bonus question in Boson Software's ExSim for CCNA. Okay, here's today's Boson ExSim practice question. Which of the following statements are true regarding physical connections in the Cisco ACI architecture? Select 2 choices. Cisco ACI is application-centric infrastructure, and it uses the spine leaf architecture. So just think of this as spine leaf. We have 5 choices, A, B, C, D, and E. Which 2 are correct about spine leaf architecture? So pause the video now to select the 2 correct choices. Okay, let's check. A, each leaf node must connect to every spine node. That is correct. That is true about spine leaf architecture. B, an APIC must connect to at least one spine node. I haven't mentioned APICs because We're not specifically talking about Cisco ACI in this video. We're talking about spine leaf architecture in general. But an APIC is a kind of end host, so it should not connect to a spine node. It should connect to a leaf node, so that is incorrect. C, leaf nodes must be fully meshed. That is incorrect. Leaf nodes should not connect to each other. And same for D, spine nodes must be fully meshed. That is incorrect. Spine nodes also should not connect to each other. They should only connect to leaf nodes, and leaf nodes should only connect to spine nodes. Okay, E, each spine node must connect to every leaf node. That is also correct. So these are two important points about the spine leaf architecture. Each leaf node must connect to every spine node, and each spine node must connect to every leaf node. So I'll click on Show Answer, and here you can check Boson's explanation. Okay, and there are some references down here, including a free Cisco documentation reference about Cisco ACI. Okay, so that was Boson Software's ExSim for CCNA. As I've said many times before, these are the best practice exams for the CCNA, and I highly recommend them. If you want to get Boson ExSim, please follow the link in the video description. There are supplementary materials for this video. There is a flashcard deck to use with the software Anki. There will also be a packet tracer practice lab, so you can get hands-on practice. In this case, although we didn't cover any configurations in this video, I will take the opportunity to demonstrate an important concept for LANs regarding the interaction between spanning tree protocol and FHRPs such as HSRP. That will be in the next video. To get the free flashcards and lab files for the course, sign up at the link in the video description. Before finishing today's video, I want to thank my JCNP level channel members. To join, please click the Join button under the video. Thank you to Kwa, Dragos, Tanvir, Chalzetta, Gerard, Tom, Samil, Scott, Martin, Tebogo, Anand, Pavel, Abraham, Sergey, Njoku, Victor, Suki, Kenneth, Seamus, Brandon, Marcel, Coney, Donald, Gustavo, Prakash, Nasir, Erlison, Marco, Ed, John, Funny Dart, Velva Jacob, Boson Software, Devin, Jonathan, and Vance. Sorry if I pronounced your name incorrectly, but thank you so much for your support. This is the list of JCNP level members at the time of recording, by the way, July 3rd, 2021. If you signed up recently and your name isn't on here, don't worry, you'll be in future videos. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. That's all for now.